Hello everyone, this is Top Dev. Today we are going to be doing LeetCode question 226 invert binary tree. This is an easy LeetCode question, and indeed it is easy. It is a recursive type question, as a lot of a lot of tree questions lend themselves, even graph questions lend themselves to recursion. And so the premise of this question is we're given a root of a binary tree. We want to invert the root and return, we want to invert the tree and return its root. Okay, this is a giveaway that we're going to be returning the root of this tree. So basically we're going to start at the top of the tree and we're going to modify it down, but at the very end we still want to return the top of the tree. And just looking at this briefly, we can kind of see what's happening here. We could see that the 2, with this example, we could see the 2 was now what was the left is now the right, and what was the right is now the left. And likewise for the subtrees of those nodes, what was the left is now the right, and what was the right of 2 is now the left of 2. Likewise for 7, what was the left of 7 is now on the right, and what was the right of 7 is now on the left. And we're returning that output. Given another example, we just have a 3-node tree here. We have a 2, a 1, a 3, and we're quite frankly just swapping them. Okay, if I pull up my paper here and I kind of wrote this out, we're given a binary tree and we want to transform it, and by way of inverting all of its subtrees and swapping out the left with the right and the right with the left. So check this out. The way that I look at this initially is I say, okay, we're starting at 1. What are we doing from there? We are basically taking, at first I thought, okay, we're going to swap the value of this with this, and the value of this with this. But no, that wouldn't actually work because we could see that the 6 and the 7 are in the right tree, and over here they're actually in the left tree. So we kind of have to do this as a whole, meaning starting at 1, we have to then say 1 dot the left subtree of 1 is now the right subtree of 1, and likewise the right subtree of 1 is now going to be equal to the left subtree of 1, all with its subtrees inverted as well. And that's why recursion comes to mind for this algorithm, because we're literally going to be going from 1 to 2 to 4, and let me draw that better. We're going to go to 2, and then from 2 we're going to go this and this. We're going to call the recursive algorithm on its subtrees, and then likewise we're going to call the recursive algorithm on 4's subtrees. So you can kind of see the recursion happening here. Likewise with this, we call the recursion algorithm on this, and it's going to call it on this and this. And basically what it's doing is it's swapping them from the right to the left, and the left to the right, from the left to the right, and the right to the left. And as you can see, that's exactly what's happening here. There is one case that I would consider is what happens if we're at the 7 and we want to swap the 7's subtrees. And so let's say 7 has no trees here, and so we want to swap null with null, or if you're working with Python, it's none. That would be totally fine, right? It would be totally fine to say, well, it was already none. The left tree was already none, so swapping it with none is okay. And what we can do is we can call this our base case. Our base case. Okay? Base case is when the tree, let's see if I can draw that again. The tree is equal to none. Okay? I also thought of another case. Like, let's say that the tree was not equal to none, but we have one side of the tree, it has a value. The other side doesn't. Now, what would that happen? What would happen there? Well, still, our algorithm would work. There's really no special case that we have to take care of here. The 8 is going to go over here, like so, and the null value is going to go over here, like so. And that's it. So really quite a simple algorithm. This is actually a great introduction to, I think, trees. And it's also a great introduction to recursion with trees. So let's get into the algorithm. So like I said, we have our base case here. And our base case is going to be when the tree is equal to none. So when if not root, we're going to return none. And then what we want to do is we want to say the self dot right is equal to, the root dot right is equal to self dot invert tree of the root dot left, right? The right side of this tree, if I delete some of this stuff, we're saying the self dot right, so this right subtree right here is going to be equal to the inverted value of this subtree. And then we're going to say root dot left is equal to self dot invert tree of root dot right, right? Isn't that how we're going to do it? That would make sense, wouldn't it? So let's look at this real quick. So the root dot right is equal to the inverted value of that. So really what we could do is we could say that this was put over here and then this was put over here, right? And this is now on the right side. And so now we're saying the root dot left, this value, is going to be equal to the inverted value of the root dot right. So it'd almost be like we were taking this and putting it over here. So now we would have duplicates. Like this would be gone, and we would now have a duplicate of that, but it would be inverted back to its original value. So it's almost like this is what it would look like. And obviously that's not what we want, because what's happening is we're setting the root dot right here, and then to the inverted tree of the left. And then we're trying to set the left equal to the inverted tree of the right, but we just set it right here, so that's not going to work. What we're going to do to solve this is use a temporary variable to save the previous state of the right root prior of the tree that is the right of the root. We're going to save the state of the right root prior to assigning it to the inverted tree of the left root. Okay, so we're going to use a temp variable. We're going to set it to root dot right, and we're going to use that because this is going to be the original value of the root dot right. We're going to set root dot right equal to the inverse of the root dot left, and then we're going to set the root dot left equal to the inverse value of the original right. And then lastly, we're just going to return our root. And so looking over this, what is our time complexity? Let's derive our time complexity out of this. Well, what are we trying to accomplish? We're saying we're trying to swap the trees. So starting at the root, we're going to need to swap this tree with this tree. Swap this tree with this tree, Swap this tree with this tree. So it looks like we have to touch every node. And you'll notice, actually, it's quite clear here that every node here has been swapped, has been touched in some way. So that leads me to think that our time complexity would be big O of n time, where n is the elements. We'll just leave it as that in the array, in the tree, okay? And then our space complexity, well, if we look at this, we're not really storing any auxiliary functions or anything like that, but what we are doing is we are inverting the tree. And so we're saying, starting at the root right here, we're saying go here, then go here, then go here. So we're going to have to make at least this many recursive calls, right? And then obviously we're going to go right here, but there's nothing here. So I believe that our space complexity is going to be the height of our tree, right? Because we have to have this many recursive calls. This is the first recursive call. Well, rather, this would be our first recursive call. Then it would call this one. Then it would call this one. Then this one. Then this one. Okay, so I'm going to leave this as the height of our tree right here. All right, so the height of our tree is h. So space where h is the height of our tree. Let's review our code before I submit it. In interviews, if you don't know this, you're not able to submit your code. So you literally have to run through it just line by line. So we're saying if not root, then we're going to return none. So that means that we are trying to call like down here. Like if or we're trying to call like maybe this one right here. This would be none. And then we're going to set the right root, the right tree to a temporary variable. We're going to set the right to an inversion of the left, which is the same function here. And then we're going to say the left is equal to an inversion of the original right. It looks good to me. Let's submit it. Succeeds. It is rather efficient. It is rather space conducive to not using a lot of space. And I hope that helped.